Let's talk about moments. Maybe you've seen this before in physics. You'll see it again in dynamics and some of your other mechanics classes. This is about more than moving. It's how hard something is to bend. It also goes into moment of inertia. So this is the tip of the iceberg, what you're going to see here, and the better you understand it, the better you'll be in a lot of classes coming in the future years. So we're looking at how hard it is to rotate something. And that's going to be dependent on your lever arm, the length of your lever arm, and on the magnitude of the force coming down. And there's this perpendicular relationship here that we're going to use cross products to find. What is a moment of a force? Any force that is applied to a rigid body causes the body to translate or rotate, or both. The tendency to rotate is caused by moments, which are created by a force applied some distance from an axis of rotation. This is a really simple cartoon, but these principles are going to apply for all of the problems. So you're going to want to really pay attention to what the system is trying to rotate around. And when you figure out what it's rotating around, that's how you're going to define this distance, this lever arm, between what it's rotating around and where the force is applied. So here we have a force, and our force this time around has both an x component and a y component. And we want to ask ourselves a question, which part of the force is going to make it rotate? Looking at the x component, this is pushing and pulling. So this would create translational motion or straight line motion. But it's the y component that's going to rotate it. And pay attention to this 90-degree angle here because that's going to be really important. Cross products. We find the component of the force that's perpendicular to this lever arm by using a cross product. So two different things. We have our force in here, our force with an x and y component, and we also have a position vector. Here is our position vector. And it's not just a magnitude, you want to know what direction it goes to. The direction of this position vector, when we plug it into the cross product, is going to be from the axis of rotation to where the force is applied. So remember the direction of this arrow, from the axis to where the force is applied. And here is the component of the force. I should draw it over here where it's actually applied. This little perpendicular combination of the force and the position vector, this is what creates rotational motion. And this is the motion we have to stop in statics to keep something stable. So I think you've probably had cross products before, but I wanted to walk through where this came from just one more time so you can see it. Let's create a system that has a position vector that's kind of an arbitrary position vector with an x and y component and a force that's an arbitrary direction for the force, and walk through finding the moment from this random position vector and random force. So what we're going to do, say this is a big piece of plywood or something, and we're going to be rotating it around this bolt. Okay, so we have a nail or a screw or something in the plywood, and then over here, this is where the force is applied. So someone is going to be pushing on this board over here, and it's going to try and rotate it around this bolt. So we're going to see what kind of rotational motion this R and F combination are going to create. The first thing to do is to split everything into x and y components. For the cross product, we're going to know the x and the y components of our position vector, again, from the axis of rotation to where the force is applied, and then we're also going to split our force into its x and y components. The next thing to ask, which X and Y combinations create rotational motion, and which way is that trying to rotate? Combine the X component of the position vector with your Y component of the force, and that perpendicular combination is going to rotate it counterclockwise. And you can either apply the right-hand rule, or you can think of it like a bolt. So if you're unscrewing it and it's coming up out of the board, that would be the positive direction. So counterclockwise is positive. So positive moment created by positive Rx and positive Fy. Okay, let's go to the next combination here. If we look at the Y component of the position vector and combine that all the way over here with the X component of the force, and we're looking at the line of action of the force. So it doesn't matter that that X component is all the way over here or if it was back, just so that it's the line of action of that force that we're trying to connect with. So position vector up to the line of action of that X force, and this combination is going to create clockwise rotation. If we were screwing this screw, this would be righty-tighty. We're pushing it into the board, backwards into the board, so that would be our negative rotational. So either righty-tighty, or if you did a right-hand rule, your thumb would be sticking back into the board. This would be a negative combination. Let's plug all of this into our cross product. R comes first, and then F. So you're going to put the X, Y, and in 3 dimensions, this will turn into RZ. The force, break it into all of its components and put those components down here at the bottom. And this is why it's called a cross product. We're combining the X and Y axes. Okay, these are the 2 chunks that are perpendicular to one another. And if you look at the Rx-Fy combination, that's what created a positive counterclockwise motion. Then if we looked at the R-Fx combination, this guy created a negative rotation. This guy created that clockwise rotation. And so we have plus over here, negative over here. And this, adding these together, finds us actually another vector. We say this is going to happen in the k direction. So the vector for the moment is describing the axis that we're rotating around. Like the vector for a force describes which direction the force is going in. The vectors for moments that we're talking about, those vectors describe the axis we're rotating around. And in this case, we're rotating around the k-axis. It's coming straight out of the board at you. Here's another way to find the moment. Instead of breaking everything up into X and Y components, we could have broken our force into which piece of that force is just pulling and pushing on the nail and not rotating, and which part of the force is perpendicular to that lever arm and is actually rotating it. And if you look at the angle between the force and your lever arm, your position vector, sine of that, the opposite side of that, that's the perpendicular piece that's going to rotate it. So we can calculate the moment from the cross product or get the same exact number if we know that angle. Sometimes it's easier to calculate a cross product because everybody gets really good at breaking everything into X and Y components, and sometimes it's just safer to go through and write out the entire cross product. Sometimes it's better to use the angle, or maybe it's on a test and you want to be sure you got the right answer. You could calculate it both ways and make sure it's the same thing either way you go. So these 2 methods are going to give you the same number. Here's just one more way to think about that RF sine theta combination. So whether it's FR or RF, here's our angle. It's the same angle over here on the other side, and this time what's opposite to that angle is a chunk of that position vector. So if we break the position vector up into which piece of that position vector is lined up with the force and which piece of that position vector is perpendicular to the force. So that's also opposite the angle r sine theta. So whether it's r sine theta or f sine theta, they come to the same numerical value. Cross products are f sine theta, fr sine theta. Either way, these are all equivalent to one another and will all give you the same number. Walking through the whole x, y, z cross product, so we have our position vector up here on the top and our forces on the bottom. If we look at what's happening in the I direction, so how much of this is trying to rotate around the x-axis, and that's going to be ry, fz, minus rz, fy. So left to right minus right to left. For the j-axis, what's going to rotate around the j-axis, this time you're going to start at the right and go to the left. rz times fx minus rx times fz. zx minus xz. The k direction. The k direction, you're going to go left, right, minus right, left. So rx, fy, minus ry, fx. What we have here is a crate. The crate has a mass of 80 kilograms, not a weight, a mass. We're going to have to multiply that by 9.81 to get a weight out of it. So that's going to happen right in the center of that crate. Find the moment produced by the weight around point E. So it's going to be rotating around point E, and what's trying to rotate it is the weight falling down. So that's part A, and then part B. What is the smallest force applied at B? So B is up here at this corner that would create a moment of equal magnitude and opposite sense around E. Okay, so the weight wants the crate to fall down, and we want to put our hand up here at this corner and stop it from rotating around E. Let's just think about this in 3 dimensions for a second to be sure everyone realizes what the moment is describing. So when we say the moment around the z-axis, that's because the whole crate is trying to rotate, not around a point. We only see the point over here, but it's rotating and around an entire line. So this is what it's rotating around. As we get started, let's go ahead and draw in the line of action of the force. This is going to help us see the shortest perpendicular distance between what we're rotating around and where that force is. And I can draw this position vector to any point along the line of action. So I could have drawn it up to the center of the crate or down, but drawing it out right here, this gives us right off the bat that perpendicular relationship. Setting it up in Excel. I'm just using a different cell for the XYZ components of my position vector and XYZ components of my weight. So from the axis of rotation to the line of axis of our force, we're going over 0.25, and you had to kind of study the dimensions for this. So if this is 0.85 and this is 0.6, take the difference, then you get this is 0.25. So we're going in the positive I direction, 0.25. And then our weight is going down in the negative J direction. We have to multiply it by gravity to turn mass into a force. And when we do this cross product, we get 0.25 times negative 80 minus 0. And this is rotating in the K direction. It's actually in the negative K direction if it's going clockwise. So if it was a screw, you'd be screwing it into the board. It's going negative back into the board. An example showing all of the different possibilities of how we could have drawn this position vector, and it comes out to the same way, either either time. So let's say instead of going straight out, we drew it to the center of the crate, and that makes sense because that's the center of mass, that's where the weight. So if we went to the right 0.25 and up 0.25, so now I have those two components. I have to find a new position vector, but it's still going to our weight. And you can see if I do this cross product, I've got a 0 down here. So the cross product ends up being the same despite what I have in my J column. So I could put anything in that J column. I could define that position vector however I want, just so long as the X component is a 0.25. You'll get the same moment. And this works for any situation. So remember, we're looking between the axis of rotation to the line of action of the force. And sometimes, depending on what dimensions they give you in the problem, it's easier to go to one point versus another point. So you can find anywhere along that line of action will give you the same result. Part B. So we want to be able to find the smallest force applied at B, all of this stuff in blue up here, that will create a moment equal magnitude and opposite sense around E. So it's team red versus team blue, team clockwise versus team counterclockwise. And to figure out what the smallest force is, so it's all going to be applied at B, but there's a lot of different directions that we could apply that force with. So you could push straight up, you can push straight over, and all of this is going to create some kind of a counterclockwise motion, but we want to be lazy. We want to find the easiest direction to push on B with to stop this motion. So which direction would be easiest to create that motion? So just like we add forces together to get 0, in Chapter 2, we're going to add moments together to get 0 to maintain static equilibrium as well. And remember, the moments are a vector, just like force is a vector. The only difference is the vector for moments is describing the axis of rotation versus the vector for forces is describing the direction of the force. So in two-dimensional problems, what it's rotating around the z-axis coming out of the board. So we're really paying attention to what's happening in the z direction. And if we add together this combination, so the weight is trying to rotate it around that z-axis, and our force up here at B is also going to be rotating it around the z-axis. So we're going to add everything in the z direction, everything that's rotating around the z-axis, and pay attention to the signs here. So clockwise is negative, that's screwing it into the board, it's pushing it back into it, negative. And then our blue counterclockwise force is going to need to be positive. So it's going to need to be screwing it out of the board. So left hand is out and positive, righty-tighty is in and negative. Let's write out the cross product for each pair of R and F. So this first cross product is for the first R cross F pair. We have our position vector coming over 0.25. Remember, 0.85 minus 0.6, that's 0.25. That's in the X direction, and we're going from the axis to the force. So we're pointing to the right, that's going to be positive. And then our force in this case is the weight acting down. So it's going to be our mass times gravitational acceleration, 80 times 9.81, and we get that negative 196.2. Okay, so this combination that's trying to rotate it, and you'll notice that negative sign makes it negative. Okay, this is rotating it in the clockwise direction, which pushes it back into the board, so that gives us our negative moment in this direction. And we have to get something equal and opposite to stop this rotation from happening. So here is our second pair with our position vector coming from E up to B. So over here at our cross product, we're going to the right 0.85 and we're going up 0.5. That's just the dimensions of the crate from E to B. So positive, positive. And our force up here at B, this is what we're going to solve for. So we don't know what the X component is. We don't know what the Y component is. We do know that that force needs to add to the same magnitude as what was happening from the weight. So we need to get that 196.2 no matter what we do. Writing out the equation for this cross product, so we have everything going on the red side to create that clockwise rotation. And we also have everything going on for the blue side, and this we're going to just keep in terms of X and Y instead of plugging numbers in. And remember, the point of this is to create an XY combination that produces the smallest force on B. We want to make life easy on ourselves. I'm going to rearrange that cross product equation so we have all the Y's on one side and then Fx on the other side. And a good way to kind of get a feeling for what this cross product is telling us is to put it into a graph. So if we graph Fx as a function of Fy, we'll be able to see those combinations and where the minimum happens. Here we are in Excel again. Excel is a great tool for graphing things out. I'm just going to make a column for the X and Y component of our force and the total force and the angle up there at the top. I'll start by just picking a random increment and creating a column of numbers for X. And then I'm going to plug those numbers into our equation that we've created for the force in the Y direction. Instead of Fx, I'm going to grab that column of Fx values. So there's our equation. If you just double click on the lower right hand corner, it'll fill that equation in all the way, and we don't have dollar signs, so it will update the cells that it is calculating that Fy from. Okay, if we have Fx and Fy, we can get the total force, just a squared plus b squared equals c squared. So square root of Fx squared plus Fy squared, and we can copy that down as well. And I want to get this total force as a function of the angle. Turn it into degrees. Again, Excel uses radians instead of degrees. And I am just grabbing the arctan of X over Y. Okay, once we have all of those numbers set up in a table, I'm holding the control key. If you highlight a column and then hold the control key down, you can skip columns. Whatever is in the first row, that's what it's going to graph in the x-axis, and the subsequent rows end up showing up on the y-axis. This is just a scatter plot graph. I'm going to go ahead and change our angle around to give just the magnitude of it. That's what we really need here, is the magnitude. That little plus, you can add axis labels, so we have theta along the x-axis and force along the y-axis, and you can see where the minimum happens on this graph. So this is kind of a graphical solution. You can see right around 30 degrees, that's where that force is hitting a minimum. And you can kind of play around with that Fx number and see how those numbers change around for kind of a numerical solution to find where that minimum happens at. Let me just go through an analytic solution instead of just numerically poking around in Excel. I'm going to start by clearing my variables out. F will be the total force, Y will be the force in the Y direction, and X will be Fx, the force in the X direction. I'm going to just put in that equation we've been using for the force in the Y direction as a function of everything in the X direction. And I'm going to get everything just as a function of that force in the X direction. So the overall force as a function of what is happening in the X direction, I'm just using an a squared plus b squared equals c squared thing here. So fx squared plus fy squared, and that's going to give me the overall force that we're pushing at B with. And I'm going to graph it out in Mathematica. This is just how we graphed it out in Excel, only I was graphing the angle instead of the x component. So here is the overall force as a function of what's happening in the x direction. I want to find the minimum. The minimum is where the slope goes to the 0 or where the derivative goes to 0. And Mathematica will solve this for us. It does the calculus for us, solves for where the minimum is for us. And then we can just plug this value for where the minimum happens into what the y component is, and then we can use those two components of our force to find the angle that this is going to happen with. Mathematica uses radians, just like Excel uses radians, so convert that over to degrees, and we're just looking at the angle in between that x and y component. So there would be the exact value. We're looking at a force of 100.874, and this would give you an angle up there of 30.4665. I want to walk through this graph and make sure everybody has a sense for what's physically happening and what this is actually describing here. Along the x-axis, this is the angle that the force is making with the vertical. We're looking at the force that's pushing up here at this point B. Over here at this side, this would be an angle of 0 where the force is vertical, so you'd have to really push up. So you'd have a large force over here, and then as you start opening that angle up, the force ends up being smaller and smaller that you have to apply to stop it from rotating around E. And around 30 degrees, this is where the force is a minimum. And then as you keep opening that angle up more and more, all the way up to 90, you end up having to apply a larger and a larger force to keep it from tipping. So the ideal minimum force is going to happen right over here. Rather than going through the pain of analytic and numerical solutions on Excel and Mathematica, the other way to solve this is graphically. And by graphically, I mean you're going to look at the picture of this and think through intuitively what the answer should be. Remember, part of this force is going to be creating rotational motion, and part of this force is going to be creating translational motion. If we want the entire force to go into nothing but stopping rotation, we want the entire force to be perpendicular to this position vector. And this is something we're not deriving it numerically or analytically. We're just looking at the picture, looking at the free body diagram and thinking through what these angles should be. So the easier solution is to look at the picture of it and think through the angles and realize that the minimum force is going to happen when it's perpendicular to the position vector. Perpendicular to the position vector. Can you figure out what that angle is? Now we're given some dimensions for our crate, so we can get dimensions for our position vector. Okay, so this is going to be 30 degrees, 59 degrees. The easiest way to find angles, look for 90-degree angles and realize these two guys have to add together to 90. These two guys add together to 90. So just start filling in what you can and walk your way around. And sure enough, that is the same angle that we solved for in Excel. So what is the magnitude of this force? Let's just split it into its x and y component using the angle we have. So the x component, that's opposite that 30 degrees, that's our sine, and it's going to the left, so it's going to be negative. And then our y component is adjacent to that 30 degrees, so that's our cosine. So here we have our cross product, I times j minus j times I. We have everything, instead of fx and fy, everything is now in terms of just the overall force. and we can solve for what our force is, and it ends up being 198.98 newtons, and we can either label that angle as 30 degrees or we're coming up 59.53 degrees. So either way, draw a little vector next to it to describe what that angle is, if it's with respect to the horizontal or the vertical, because sometimes that's a little confusing. In case you want to play around with that Wolfram Alpha site, hopefully you've already played around with this site in some of your math classes. So we could have typed in that equation and asked it to solve for our force for us. That's how you would type that one in if you don't want to do the algebra. This isn't a math class, this is a statics class, so really whatever math software you want to use to do the calculus and algebra for you, and from here on out you're going to want to use some kind of a math software because you don't want to do all this stuff by hand. And just one more note, as you're getting started with this stuff, I'd highly suggest that you write out the entire cross product. Again, everybody's kind of used to splitting everything into their x and y components, and it seems to be easier for everyone to break everything into x and y components and walk through the entire cross product than trying to figure out what the angles are initially. So you'll be a little bit safer by starting out just putting the cross products for everything in this. More examples. The best way to understand this stuff is just work example after example after example. So let's start out by just reading the problem statement. It is known that a vertical force of 200 pounds is required to remove the nail at C. So what are we talking about? Okay, so there's a nail at C, we have a crowbar, and it's going to take 200 pounds. So this nail is in here and we're going to have to pull up, straight up, vertical force of 200 pounds here to remove it. As the nail first starts moving, determine the moment around B. Where's B? Okay, so this is where it's pivoting around, is B. So we're going to find the moment around B created by the force exerted on the nail. So 200 pounds here is going to create a moment at B. And after we figure that out, the magnitude of the force P that creates the same moment. So we pull over here at P, and this creates a moment around B, and this is going to also pull up around C. And then we're going to be looking for the smallest force that creates this moment. Okay, so how should you pull on this crowbar? Should you pull straight across or down or up? So this is going to be another similar problem to that crate. Once you see the solution for some of them, you'll start to see patterns develop in these, and it's going to be the same pattern for various different systems and geometries. One thing to do is to read through your problem statement with a highlighter in your hand. Print it out so you don't have to copy it by hand, and then just start highlighting all of the pertinent information. And then once you highlight the numbers on here, draw what's happening on the picture itself. So this is the first steps in creating a free body diagram. So we have a vertical force. Vertical means straight up and down at the nail at C. And if you just take some time initially to think through physically what's happening in your system, that's going to go a long way to getting you to that fast geometric solution where each one of these is a puzzle. And the more time you spend thinking through what's actually happening and which way the forces are, that's going to give you a shorter, faster solution to these problems in the long run. Okay, so vertical force, we have it labeled. You can use the Excel file that I have set up for you, or you can do this by hand. This is another thing to realize. Problems that have part A, part B, part C, part D, they're not trying to make more work for you. They're trying to give you the steps. So in order to jump all the way to C and figure out what force and what direction is that force in, if you start with A, this is walking you through the steps of that problem for how to get to the final piece of information that you're really interested in. So here's how to set that up in Excel. First, we're going to look at the force at C creating a moment around B. Our position vector is going to be from B to where the force is applied. So we're going -4 inches in the x direction. So here's our position vector. And the force that's going to be required is this 200 vertical force. So we're going positive J direction 200. And the moment around B, so this is the first chunk of it, part A, is just -4 times 200. And you can just click on this cell times this cell, minus the zeros, and you get your -800 force. And this is in the K direction. So the rotation is happening around an axis coming straight out the board at you. So it's wrapping itself around the K direction, and that's a negative moment clockwise, and this is screwing it into the board, righty-tighty, negative moment in the K direction. Part B, find the magnitude of the force P that creates the same moment about B if alpha equals 10 degrees. So let's label what they give us here. If alpha is 10 degrees, we're going to find out what this force is if we're going to create 4 times 200, an 800 pound-inch moment going on over here. Okay, so here is the nail, and it's going to be pulled up by R cross P. Break everything into X, Y, Z components. Let's look at our position vector. So we're going from B up to where the force is applied. They give us 70 degrees. They also give us the length of our crowbar is 18 inches. So if we make just a little triangle here, we can see the X component is going back. It's going to be negative. That's the adjacent side to 70 degrees. So cosine. Here's our X component, -18 cosine 70. And then our J component is going up, 18 sine 70. So negative and up. There's our position vector. And now we have to break our force into its X and Y components. We'll use that 10 degrees. The X component, that's adjacent to the 10 degrees. That's going to be cosine. And the Y component, that's opposite the 10 degrees. So that's going to be the sine component. Again, really watch those signs. Positive in the X direction, negative in the Y direction. If we solve this moment equation, so just crisscross, we're going top to bottom minus bottom to top. So the 18 cosine times P sine minus 18 sine, P cosine. And that's going to add together to what that nail is doing. 4 times 200, 800. So if you solve this for what the force needs to be, you end up getting a force of 50 pounds to create 200-pound pull on the nail. And that's the point of a crowbar. That's the point of a lever arm, right? You have this nice big lever arm, and you can pull it with a very small force here. Only 50 pounds here creates big 200-pound over here. So that's nice little mechanical advantage going on right there. And you can see that advantage 4 to 8, okay? So that lever arm mechanical advantage translates into a force mechanical advantage, 50 to 200. Part C. Let's find the smallest force to create that 4 times 200 moment around B. What's the angle here that's going to create the smallest force? Rather than going through analytic and numerical solutions, just look at the geometry, use your intuition, and remember that 90-degree trick. If our force is 90 degrees with a lever arm, then 100% of that force is going to do nothing but rotate it. Anything that's not 90 degrees, it's not rotating it. It's just pushing and pulling on it, and it's wasted effort. If the point of all of it is rotational motion, then we want all of our effort to go straight into rotational motion. So if that's 90 degrees, take that 70, 70 over here is 70 up here. So we're looking at something coming up at 20 degrees. And to figure out what that force is, rather than breaking everything into x and y components, it's just going to be the position vector times the force. They're already 90 degrees with one another, so you don't have to go through that cross product at this point. So 18 inches long times that force, that is what you're pulling on the crowbar with, and that's going to have to create 4 inches to 200-pound force. So 4 times 200 on the left-hand side of B is going to have to be equal to P times 18 on this side. And we're looking at that 90-degree angle, so we have P as 44 pounds, and it's going to be at 20 degrees. Whenever you get the answer to something, there's two pieces of that vector, the magnitude of it and the direction. So always report both the magnitude and the direction, and you can draw a little vector next to the direction so we know that 20 degrees is with respect to the horizontal. Three-dimensional example. Don't worry, the three-dimensional ones, some people actually think they're easier. So we'll see. Okay, before the trunk of a large tree is pulled down, cables AB and BC are attached as shown. Okay, so we're going to pull this tree over, and we want to make sure it doesn't fall on your car or fall on your house. We want it to, it looks like they're trying to pull it kind of forward. So these two cables, AB and CB, are going to help pull the tree over and pull it in the right direction. Knowing the tension in cable AB and BC are 555 newtons and 660 newtons. Find the moment around O. This is the moment around the origin of our coordinate system. So we're going to uproot the tree right here at the ground. And the resultant force exerted on the tree by the cables at B. So B, this is where the cables are actually pulling at the tree. The force is applied here, rotation is happening down here at the ground. So force is up here, rotation happening at the ground. The vector describing the moment always seems to be a confusing point for everyone. So let's split this apart and think through what each cable is doing to the tree. The first cable over here is pulling down and forward, and what this would create is a rotational motion mostly around the x-axis. So the force at B from this cable, and we're going up the tree trunk and then pulling at B, this is going to rotate it around the x direction. Think through the same thing with the other cable. So the other cable pulling at B is going to create a rotational motion around the z-axis. If we add both of those together, we end up with a rotational axis that's kind of at 45 degrees. Now the cables aren't exactly on the coordinate system, but this is the basic idea, is the tree is going to fall forward and you don't want to park your car right here. Okay, so it's going to be a combination of rotating around the x-axis and around the z-axis. And here is the vector describing what we are rotating around. So it's a little bit in the x direction, a little bit in the z direction. Both of them together create this new vector. And this vector addition, this is just like adding force vectors or any kind of vectors. So you can add the x direction plus the z direction, and this is head to tail, head to tail. Here's the the magnitude of the overall moment that is created from this. So the moment really is vectors, and those vectors are describing the axis that you're rotating around. Before we can take the cross product, we have to split everything up into its x, y, z components. Let's split cable AB up first. We have a force of 555 newtons, so I'm going to fill that in over here. And we're going to go through looking at the distances of our cable. We'll use our cable to find our unit vector, and then our unit vector to split apart our forces. Okay, so here's our cable. We're going back in the x direction just a little bit. There's our negative 0.75. Y, that's coming down the tree trunk, 7 meters. We're coming down the tree trunk 7 meters. And then Z is coming forward, and that's our 6 meters right here. dx, dy, dz, find the overall distance. So that's x squared, y squared, z squared. Take the square root of it. So that's the length of our entire cable. And then to turn this into our unit vector, remember the unit vector is just the ratios. So 0.75 over the total length, and 7 over the total length, and 6 over the total length. And our unit vector has a length of 1. We then take our unit vector and use that to split our force apart. So 555 times 0.081, there's our x component. 555 times 0.75, there's our y component and our z component. And you can check to make sure x squared, y squared, z squared gives you back that original force at the end of it. Same thing for the next cable, BC. This is where it's nice to set it up in Excel because you can just copy and paste those same tables around, fill out a couple different numbers. X direction, we're coming forward 4.25 in the x direction. Y, it's the same tree trunk, we're coming down 7. DZ, there's our z component, so we're coming out 1 meter. There's our cable distance, here's our unit vector, and we can split this force into x, y, z components. Before getting the answer for any of this, think through intuitively what it should be. So which way is this tree going to fall again? Where is it rotating around? What's the axis of rotation? And that's where are we taking the moment around? That's the ground. So it's going to be rotating around the ground. So moment really is a stability. A lot of failures happen by something rotating around a point. This is describing anything that's falling over. It's a moment and it's a rotational fight that you're doing to keep things stable. Each force creates its own moment. Let's look at cable AB first. So the position vector from where it's rotating around to where the force is applied. So we're going up that tree trunk. So here's our position vector. We're going right up the tree trunk from the ground to where the force is. And the force in this cable is pulling down and forward. There's the X, Y, Z forces that we split apart previously to take that 555 and split it into its X, Y, Z components. Once we have this in our cross product, we're just going to be walking through. There's a lot of zeros in here. We end up getting something mostly in the X direction, just a little bit in the K direction. And you can look over here, see how this cable is rotating it mainly around the X axis. So it's going to be pulling it straight forward, rotating it around the X axis, and it's not quite on the Z, so that gives you a little bit of rotation around the Z axis too. Same thing for the next cable. Which way is this cable trying to rotate? So remember, this one's kind of pulling in the X direction, and that's going to rotate it around the Z direction. So you'd expect for this to be the large magnitude that this guy's rotating it around. Okay, so once again, we're coming down the tree trunk. Axis of rotation, to where the force is applied. So there's our position vector, 0, 7, 0. We had to split that 660 newtons into its XYZ components. So there's the force split up into its XYZ components. Then crank through the cross product, see what's in the I direction, what's in the J direction, what's in the K direction. And at the very end, we're going to take the moment generated by AB, the moments generated by BC, and add these together. So we add everything in the I direction together. Nothing happening in the J direction. Why is the moment in the J direction 0? That's because there's no distance. The cables are attached to this axis. So it's, you know, the tree is not going to be rotating around the Y axis at all. It's going to be around the X and the Z axis. So this ends up being 0. And here is the K direction. So that is, when you add these guys together, you get something kind of big in the I direction from AB. You get something kind of big in the K direction from BC. And when you add these two together, here's the overall axis that it's rotating around and the magnitude of how much that tree is getting pulled around this axis. And you're going to use that right-hand rule for positive versus negative. So it's rotating around to the front. That will stick your thumb backwards and add these vectors together just like you'd add a force vector together. Hope that helped you. Let me know if you want to see some more examples like that worked through, and go ahead and watch some of the other YouTubes out there. I'm not the only one doing this stuff. We'll see you later.